Welcome to this explainer. Today, we're about to crack open the single most important technology of our lifetime. We're taking a cinematic, deep dive into the very engine of modern artificial intelligence. We are going to deconstruct, literally layer by layer, the architecture of artificial neural networks. We'll trace the journey from the wild theoretical dreams of the 1940s all the way to the autonomous, agentic systems that are completely rewiring our global economy today. By the end of this, you're going to see exactly how a collection of surprisingly simple mathematical equations can actually learn, adapt, and exhibit behavior that we can't help but call intelligent. So buckle up, we're going inside the black box.
You know, the whole thing begins with a deceptively simple, yet just profoundly audacious question. Could the workings of the human brain be reproduced in a machine? To really grasp the weight of that, we have to travel way back to 1943. Think about that. We are far, far removed from modern supercomputers. But mathematicians and neurophysiologists were already looking at the incredibly intricate biological wiring of our own minds. And they started wondering if that exact same magic, that spark of cognition, could somehow be captured in the rigid, logical, electrical realm of computation.
So, let's look at the very first attempt to actually answer that grand question. This is the McCulloch and Pitts neuron model. You had Warren McCulloch, a neuroscientist, and Walter Pitts, a brilliant young logician. And they did something absolutely revolutionary. They translated a squishy biological brain cell into a highly simplified mathematical binary model. It basically took in electrical signals, added them up, and made a strict black and white yes or no decision. It either fired a 1 or it outputted a 0. Now, this was entirely theoretical, because literally no computer on Earth at the time could run it. But right here in 1943, they established the fundamental language that AI would speak for the next 80 years.
But, of course, a theory is just a theory. How did that dream become a reality? Fast forward to 1957, and Frank Rosenblatt introduces the perceptron. This was a massive leap. He took that McCulloch-Pitts concept, but he gave it the ability to process real-valued inputs, not just basic binary ones. And here is the real game changer. The perceptron was the very first model capable of actually learning from its environment. By checking its output against the correct answer and then tweaking itself to minimize its errors, the machine was suddenly doing something entirely new. It wasn't just computing anymore, it was adapting.
Which brings us to the anatomy of a neural network: layers, neurons, and parameters.
From those early single neurons, engineers eventually figured out how to stack them into massive architectures, usually broken down into an input layer, hidden layers, and an output layer. But what exactly is going on inside those hidden layers? That's kind of the dark matter of the network. Well, it all comes down to parameters, specifically weights and biases. I want you to think of weights like volume dials on a massive studio soundboard for every incoming signal. A high weight means a particular piece of data is super important to that neuron's final decision. Biases, on the other hand, they act like a baseline threshold. They shift the decision boundary entirely, basically allowing a neuron to fire and pass on its signal even if the incoming inputs are incredibly weak or practically zero.
And if we peek under the hood, the actual math happening inside the node is brilliantly elegant. The pre-activation value, we call it Z, is literally just the sum of every input X multiplied by its corresponding weight W plus that baseline bias B. That is it. That single linear equation is the fundamental calculation powering literally everything from facial recognition on your phone to massive language models. It's just beautifully simple. But on its own, it has a fatal flaw.
Here is the catch. If you only stack linear equations together mathematically, the entire network just collapses into one flat, boring line. It would be completely incapable of understanding the complex, non-linear reality we live in. That is exactly where activation functions step in. You can picture these as non-linear dimmer switches or mathematical gates. Historically, scientists used functions like sigmoid and tan, but they had a major issue. Their signals often decayed to zero as the networks got deeper, a huge roadblock that we call the vanishing gradient problem. The network would just stop learning. But then came the ReLU revolution. ReLU simply outputs the maximum of 0 or the input. It sounds almost too basic, but it maintained a strong, constant gradient of 1 for positive numbers. It was a remarkably simple fix that essentially saved deep learning, finally allowing us to train incredibly deep, powerful networks.
All right, moving on to the engine of intelligence, how machines actually learn.
So, we have the structure, right? The weights, the biases, the activation gates.
But a freshly initialized network is basically just a brain filled with random static. How do we turn that static into focused intelligence? Well, learning in a neural network is just an automated loop that repeats millions, sometimes billions of times. First, the forward pass. Data flows through the network to make a prediction. Next, loss estimation. We compare that prediction to the ground truth to measure the exact magnitude of the error. Then comes the real magic, backpropagation. The network figures out exactly which weights caused that error. And finally, the parameter update, where the network slightly turns those volume dials, adjusting the weights to do just a little bit better next time.
To really visualize how those weights get updated, we have to talk about an algorithm called gradient descent. Imagine you're blindfolded, standing on a super rugged mountain, and your only goal is to reach the absolute bottom of the lowest valley, because that valley represents zero air. You can't see the valley, obviously, but you can feel the slope of the ground right beneath your feet. Gradient descent essentially uses calculus to find that slope, telling you which way is downhill, and you take a step. Now, the size of your step, that's your learning rate. If your stride is too big, you'll literally step right over the valley. But if it's too small, you're going to be stuck wandering on that mountain forever.
But wait, how do you actually know which of the billions of weights to adjust in the first place? This brings us to what is arguably the most legendary breakthrough in AI history, from the 1980s, backpropagation. By taking the chain rule of calculus and applying it sequentially backwards, starting from the output layer and flowing all the way back to the input layer, backpropagation assigns a highly precise fraction of the blame for the final error to every single weight and bias in the entire network. It's this incredibly ingenious backward flow of information that finally made deep, multi-layer networks trainable. Without this, modern AI just doesn't exist.
Let's step into our next section, from simple networks to deep architectures.
Once backpropagation was unlocked, the whole field just exploded. We rapidly moved from simple mathematical toys to massive, specialized architectures that could extract incredibly complex, hierarchical features out of raw data. And it's fascinating how form follows function here. For computer vision, we built convolutional neural networks, or CNNs. They use these clever sliding filters to detect spatial hierarchies. The early layers find basic edges, middle layers combine those into shapes, and the deepest layers recognize a human face or even a tiny tumor in a medical scan. But for sequential data, like human speech or text, we needed something different. So we built recurrent neural networks and LSTMs. These use feedback loops as a form of short-term memory, which allows the network to actually remember the beginning of a sentence by the time it reaches the end.
But RNNs had a pretty massive bottleneck. Because of their design, they had to process data sequentially, literally one word at a time, which was painfully slow to train on massive datasets. Then, in 2017, everything shifted. Researchers at Google introduced the transformer architecture. This was a total paradigm shift. It completely abandoned sequential processing in favor of a parallel self-attention mechanism. Suddenly, every single token, or piece of a word in a sequence, could evaluate its mathematical relationship with all the other tokens simultaneously. It broke the speed limit of AI. That parallel processing power is the exact breakthrough that unlocked the sheer massive scale of modern large language models, giving us things like ChatGPT.
But transformers aren't perfect. They have a really harsh mathematical limit. Their computational cost scales quadratically, meaning if you just double the length of the text you feed it, you quadruple the computing power required. They are massive memory hogs. So enter the next great frontier, Mamba, which is based on state space models. Mamba achieves linear scaling. It processes sequences using a highly compressed hidden state, which means theoretically it can digest millions of tokens. We're talking entire books or entire human genomes with incredible efficiency, totally bypassing the massive memory footprint of a transformer. It's a huge step forward.
Which brings us to our final major topic, AI in the modern world and the black box.
Let's take a step back and really look at where this leaves us today in what we call Phase 7 of AI history, the era of agentic AI. We are moving so fast beyond simple chatbots towards autonomous networks that can actually reason and execute complex, multi-step actions in the real world. But as these networks start powering more and more of our global infrastructure, we run headfirst into a massive paradox, the black box problem. We know the math, we build the architectures, but when a model with 1 trillion parameters makes a decision, like denying someone a mortgage or diagnosing a rare disease, the exact reasoning is deeply opaque. It's hidden inside an ocean of weights and biases.
When you add in the risks of models hallucinating completely false facts or reflecting ingrained human biases from their training data or just disastrously overfitting to noise, the need for transparency isn't just an academic problem anymore. It's incredibly urgent.
So how are scientists fighting back against the black box? They're developing a whole new field called explainable AI, or XAI. We have tools like SHAP, which actually uses game theory to precisely map out how much each individual feature contributed to a final decision. There's LIME, which builds simplified, interpretable models to approximate the complex ones locally. And then there are saliency maps, which visually highlight exactly which pixels in an image an AI was focusing on when it made a classification. We are literally forcing these incredibly complex alien models to show their work step by step so that human beings can actually build real trust with them.
And that brings us to our final thought for today. We started this whole journey by asking if a machine could reproduce the human brain. Today, by leveraging elegant mathematics, massive oceans of data, and advanced silicon, we have built architectures that genuinely mimic the shadow of cognition. But as artificial neural networks march closer and closer toward true artificial general intelligence, and as they become autonomous agents moving through our world, the ultimate question flips. What will building machines that learn finally teach us about the profound, beautiful mystery of our own intelligence? It's something to think about. Thanks so much for joining me on this explainer. Keep wondering, keep building, and I'll see you in the next one.